Hi, so my name is Jesse. I'm a student at the University of Toronto, and today we're going to be talking about mathematical logic. And so I want to note that I'm recording this after the actual talk has occurred because I forgot to record the first half. And so I'm just going to re-record about the first 15 or so slides, and then I'll edit back in the original talk at the point at which I remembered to start recording. And so there might be a little bit of it might be a little confusing for a second there, but it should be fine. So let's talk about mathematical logic. And here's the outline for the talk. And it was right around here that I started recording. So we're gonna stop. I'm gonna stop here, and the rest of the talk is gonna proceed. So the first question we're gonna answer is, what is mathematical logic? Because when I was preparing this talk, I think that was a question a lot of people wanted me to answer was, what is logic? Why should I care? Why should I study logic? And I thought that was an insanely hard question to answer, to be quite honest. And so I read a bunch of prefaces for logic books, and I looked around and I couldn't really find anything satisfying, and I still don't have a great satisfying answer. So instead, I'm going to give you what a few famous logicians think logic is. And these are their quotes. And then I'm also going to just tell you a bit about the history of logic and also some of the applications of it. And so this is a quote by Thomas Scanlon, who is a logician at one of the UCs, the University of California schools. And he says that logic is the study of formal languages and the connections between those languages and their structures or interpretations. And then this other quote, which I like quite a bit, by Joseph Schoenfeld, is he says, logic is the study of reasoning, but mathematical logic is the study of the type of reasoning done by mathematicians. And I really like this quote because it sort of draws the distinction between what is being logical, what is reasoning logically, and what mathematical logic is. Because mathematical logic, well, of course, we're reasoning logically. It talks about something a bit deeper than that. And the main fields of mathematical logic, and the ones that you'll hear about a lot, are set theory, proof theory, or meta-mathematics, it's sometimes called, model theory, and then recursion or computability theory. And the one that we're at the very end of the talk, we're going to give some examples from model theory, specifically a proof of a theorem called the Ax-Grothendieck theorem. But there are other, there's obviously, everyone knows the famous results from set theory. Proof theory used to be a big field. It's not huge anymore. Model theory is probably the big prominent field in this list nowadays, I would say. Anyways, the first thing I want to do is just talk a bit about the history of logic. And I'm starting from a weird point. I'm going to be starting from Hilbert. So, well, historically, I guess the field of logic was focused on the foundations of mathematics. So if you think of mathematics as some like hierarchy where maybe you have like calc up here, and then below calc you have like arithmetic. And I'm obviously skipping a lot of stuff. And then at some point down here, you have like your set theoretic axioms. So in modern math, it's ZFC. Usually, I guess is what people would say are the foundational axioms of mathematics. But if you were to go back to the 1900s and you were to ask them, what are your foundational axioms? They're going to say, oh, we don't know. We don't have them. And they had a set theory back then, but it was super problematic. And actually, there was a guy named Russell, Bertrand Russell, and he presented this thing called Russell's paradox. It's an R, paradox. And Russell's paradox took aim at the set theory of the time and essentially just blew it wide open. And so due to this, one of the big logicians of the time, or one of the big mathematicians overall, his name was David Hilbert. And this is David Hilbert with his glasses and his amazing hat. And he started this program, and it's known as Hilbert's program nowadays, but it was a research program. And its main goal was to essentially axiomatize all of math or show that all of math could follow from some finite set of axioms, and then show that that set of axioms was consistent. And you might have a vague notion of consistency in your mind, and that'll work for what I'm saying. And so the way he planned to do this was something that was called meta-mathematics, and I think it was the meta-mathematics that we might know today. And this project took up quite a bit of the 1920s, and right up until took up all the 1920s, to be honest. right up until 1929, when a PhD student at the University of Vienna, that you might know, essentially showed that this project was something that could never happen. It was a fool's errand. And that guy's name was Kurt Gödel. And I think everyone knows Kurt Gödel's name. Kurt Gödel is most famous for, I guess, in popular culture for the incompleteness theorems. And so there's two of them. So they're called the incompleteness theorems. And we're not going to really talk about them too much besides us using them to highlight a difference between the two theorems that we are talking about today, which are the completeness theorem and the compactness theorem. And he actually proved both of these, and these are huge results in the foundations of logic and first order logic. And he proved both of these within a year of each other, because this was his PhD thesis, the completeness theorem. It was his PhD at Vienna in 1929 or 1930, I don't really know. And then the compactness theorem was published a year later, but it was a direct corollary of the completeness theorem. And I'll present the proof of it, and you'll see how immediate it is, I guess. And so the last thing I want to mention is this is sort of like a history of like some famous names in logic, essentially. But logic didn't just die in the 1930s, and logic is actually a thriving field today, mostly in the form of model theory. But today, logic takes mathematical logic. I'm going to use them interchangeably throughout this talk, logic and mathematical logic. I'm always talking about mathematical logic from now on. But logic today heavily interacts with fields like algebra, analysis, geometry, and number theory. And actually, we're going to look at an example of an algebraic theorem, or stuff from algebra used, proved model theoretically. Logic has its hands on all of these different fields. And one really good example, I think, is this conjecture in geometry by a guy named, it was conjecture posed by Mortel and Lang. It's called the Mortel-Lang conjecture. And I'm not going to state it. It's quite a complex theorem in geometry. But if you were to look at it, the important part is that you would never think it had anything to do with logic. But in 1996, I don't know how to say his name, I'm so sorry. Id Hrshovsky, who is a logician at the University of Jerusalem, I think. Hrshovsky, that's a V. Gave a proof of the Mortel-Lang conjecture, and his proof was using model theoretic techniques. And this had been proved in certain cases, but he proved it in the most general case with model theory, which is amazing, because this theorem, and if you can go look at the statement, it makes a statement about abelian groups or something. It's completely disconnected from the rest of, it's completely disconnected from logic in the statement. And it's really amazing that Hrshovsky was able to make that connection. So that's an interesting application of logic to other fields of math. And then outside of math, mostly in computer science, logic is super applicable. And so I talked about computability theory. And computability theory was a field that was heavily developed by there's a lot of big names, but two big names that come to mind are Alan Turing and Alonzo Church. And you might know him from the Church Turing correspondence, these people. And they did a bunch to pioneer the theory of computation. And the theory of computation is super important in computer science. And I mean, everyone knows about Turing machines and stuff. And these are all super important objects of study in computability theory, which is a subset of logic. Also important in computer science, if you're familiar with programming language theory, the study of semantics is heavily influenced by model theory and uses techniques from model theory. And then I guess a slightly more obvious one is the model checking and general software verification, or formal verification of software, uses model theoretic techniques very often. So this is just like a broad overview of some of the uses of math and some of the uses of logic and some of the uses of logic in other fields and in other fields of math. And so now let's just dive into some definitions so we can start talking about logic. And so this first half of the talk will be a lot of just throwing definitions at you And then at some point, we'll start proving theorems and talking about interesting problems, and then the talk will be over. So our first definition is a first-order language. I'm sorry if I've marked up the slides a bit in advance, but a first-order language, or we're just going to say language from now on, is specified by optionally including a quality, a set of predicates of various arities, so like n-ary. This is like a binary. When I say various arities, I mean like binary, trinary, ... And so a predicate symbol in this example would be something like x is less than y. This is a predicate, less than, or actually not a quality, but any sort of relation symbol is a predicate. And then we have a set of function symbols of various arities. So for example, like f of x, y, where this is a binary function that says x plus y, and this is the same thing as like this is like the addition function. And then we have lastly a set of constant symbols, and so these constant symbols are something like zeros or 1 in the language of arithmetic, or the language of fields, or the language of rings. These are the constant symbols you usually have. And note that these sets are not necessarily like populated in a language. You can just have like empty language which has literally nothing in it, for example, besides, well, nothing. And then note that also that if we like put brackets around this and we call it, we can call this the signature of a language, and this is essentially what specifies a language. And it's important to note that ambiently, when we talk about language, we kind of have the idea that ambiently, there are all of our normal logical connectives inside the language. So we have and, we have or, we have implication, we have the biconditional, we have the negation, etc. And then we also have the universal quantifier, the existential quantifier. I'm gonna put a little star here because we don't really, and stuff like that. So this is all ambient. Every language has these. It's just that this stuff this is what specifies a language. This is just, oh, I just deleted everything. No, I didn't. So all of this stuff specifies a language, and then this is just always in a language, no matter what. We can't talk about a first-order language without it having all of our normal logical connectives, and the universal quantifier, and the existential quantifier. Oh, and I'm forgetting a set of variables. So like v1, v2, v3. These are just like variables that we can quantify over. As well as, I always thought this was silly, but we include the parentheses in the language, so, or in the ambiently in the language. So the parentheses that we might wrap around like A and B implies C, like these are in the language. That's just a small note. Anyways, let's move on to an example of a language. And so this is the language of arithmetic with a quality. And so this is important. It has a quality, and do note that I'm not stating it in the way we're specifying a language. I'm just going to say the language has a quality. And the reason for that is a little technical, and it has to do with a theorem that we're going to talk about later called the Completeness Theorem, and how it was originally proved by Godel in the 1930s. So just for now, just do note that this language has a quality, but I'm not really specifying it. And then the other things that the language of arithmetic has are a constant symbol. And this looks like I'm going to call it O. It has a constant symbol O. It has a unary function, so something that operates on one variable, S. And then it has binary function symbols, plus, cross, and less than or equal to. And what I want to note here is that when you look at these, I know that everyone who's ever done any math has like a connotation associated with the constant symbol, or I mean like the addition symbol, or the multiplication symbol, or the less than or equal to symbol. But what's important to note is that this isn't, like when we're talking about the language of arithmetic, that's not the connotation that these have. We don't care about the connotation because this is uninterpreted. Like I could tell you that addition is actually defined like if x plus y is the same thing as saying like 7 times x all squared or something, and like this is the definition of x plus y, and you're just gonna have to take it, right? Because we're leaving this language uninterpreted. And so what we say is actually these are symbols in the object language. And so if you think about it, you can think about the object language as like being down here. And then above it, there's something called the meta language. I'm just going to write meta lang. And the meta language sort of looks down at the object language. And this is my way of saying it's looking down at something. It's like this, like, you know. And the meta language looks down at the object language, and the meta language can say things about the object language. And so in the meta language, which is English in our context, you know, we know that plus means, you know, adding things. So we know that multiplication is multiplying things on the natural numbers or whatever. But in the context of the meta language, all of this stuff is meaningless. And so it depends on how we interpret it. And so the next thing we're going to talk about is how do we interpret stuff? Because this is really important, because we need to give some sort of semantics to our syntax, so to speak. Because right now, all we have is symbols on a page. So we got to make sure those symbols have meaning besides, yeah, anyways. So this motivates our next definition, which is not the universe, but the interpretation function. The universe is just a small technicality, and it's just some non-empty set. And this will come in handy because this is what our interpretation function maps to. So just think of the universe as some non-empty set, like maybe like the natural numbers or the complex numbers or the English alphabet, whatever, it doesn't matter. So what we say is that given some universe U, an interpretation function I for the language L, so for the interpretation function is defined with respect to a language. It's a function. It's a function. So it takes some predicate and it maps it to a set, and that set is a subset of the language. So, for example, in the context of if in the context of like the natural numbers, if we had U equals the natural numbers, the interpretation function takes like less than, and it maps it to a set that says it's like the set of numbers such that, well, it maps it to a set that's a subset of n2. And it's the set of numbers that are such that, or a set of pairs such x, y, such that x is less than y, essentially, in the natural numbers, for example. And then similarly, we have a function, an interpretation for a function. And so the interpretation for a function gives you another function, and that function is defined on the universe. So you say you take some n-place function symbol from the language, and it gives you back a function on the universe. And it's similarly, if you give an n-place function, you're going to get an n-place function back. And then lastly, just for any constant symbol, it takes it maps some constant symbol to some function or variable in the universe. So let's look at an example of an interpretation function. Or, well, first, let's define one more little thing. And this is a notational convenience and also an important definition, and it's called a structure. And a structure, all it is it's some pair, and I'm going to use the letter M for the rest of this talk, mostly, this script M. And it's just a pair, an ordered pair of a universe and an interpretation. And this is important because it's just like nicer to talk about a pair of these two, because you always need both of them. So we always talk about a structure. But the real important one here is usually the interpretation. So let's look at an example of a structure or a model. I like to use the word structure here. So let the language of arithmetic denote be like as in the previous example that we gave earlier. And then let M be a pair of universe and interpretation such that the universe is the natural numbers. The little o is interpreted as the letter number 0 in the natural numbers in N. We interpret less than as a subset of N2, where it's pairs of Mn such that M is less than or equal to N. And this is under our classical interpretation. So it's important. This is the classical or standard. I'm going to write standard instead. Standard interpretation of less than or equal to. Similarly, we interpret I of s on n as just saying n plus 1, and this is called the successor function. And this is, if you're familiar with the piano or Robinson arithmetic, you'll be familiar with the successor. And some people just write it as SUCC, suck. Next, we have addition. And so addition is just, it's classical addition again. So it's standard addition. It's just defining n plus n. And then similarly times. And so what's important to note is that this might look like completely useless. This looks so stupid, I think, on first viewing, because it looks like all I'm doing is saying plus is plus, times is times, less than or equal to is less than or equal to, 0 is 0, and successor is successor. Like, okay, like why are you doing this? Why can't we just say it's math or whatever? It's like normal. And I mean, you could, but it's missing a point here, which is, and the point I'm trying to highlight is that sentence letters in the language are in the object language. So this is an object language. This is a character in the object language, or a symbol in the object language. Similarly, this is a character in the object language. This is a character in the object language. This is a character in the object language, and this is too. Whereas stuff like this is a character in the meta language. This is a character in English, sort of. It's a character in the meta language where we're used to talking about natural numbers, and we have a standard interpretation for things. So is this, so is this, and so is this. And I'm really trying to hammer this point home because it comes in handy in a second here. So just note that this symbol and this symbol are not the same thing, even though they look like the same thing. And right now we're denoting them as the same thing. If I wanted to change the meaning of the symbol and say, oh, this is actually m plus m, I could do that and it'd be fine. And you obviously can't do that with like the standard interpretation of addition as we understand it normally. And then just quickly, sometimes we'll informally write a structure like this where we are actually interpreting everything standardly as just this, just like a pair or like an ordered pair of the universe, and then all of the ways that we're interpreting it. And since it's all standard, we just write it, and this is super informal, but this is something people do pretty often. So moving on, these are just two important definitions I want to talk about. One sec. Sorry. So the first definition is that of a sentence. And so within first order logic, we have everything that we can write down is called a well-formed formula. And I'm going to write WFF. And so an example of a well-formed formula is like for every x, there exists a y such that pxy implies like z x or yx or something. I don't know. This is a well-formed formula. This is completely valid. But if I were to write this, if I were to just take the same formula, duplicate it, and then remove the for all x, this is still a formula, but this is a different class of formula, so to speak, because here x has no quantifier. X isn't attached to anything, and so we call it a free variable. So whereas in this, x was attached to this quantifier, so x was bound. We say bound and free. In this example, it's unbound or it's free. So this sentences with no free variables are called, or formulas with no free variables are called sentences. And then we don't have a name really for sentences for formulas with free variables, but we just call them formulas in general. And so in this talk, I'm going to be talking a lot about sentences, and the reason is, as you'll see in a bit on that it introduces a lot of ugliness into our theories, and I'm just trying to like get a quick overview. So we're only talking about sentences, as in we're only talking about things with free variables, or without free variables. I'm sorry. And then also a theory T is just a set of sentences. So it's some like for example, T could be like for all x, px, A implies B, and like there exists a y such that pxy or something. Actually, well, that doesn't make sense because that has a free variable, py. There. That's like a theory T. That's all. And some authors go a little bit further. And if you read a book like Enderton's Mathematical Logic, he goes a bit further in how he defines T. Anyways, moving on. We need to talk about the issue of truth. So in zero order logic, I like to call it zero order, but people call it sentential logic, or just regular old like symbolic logic without quantifiers. When we ask if a formula is true, it's a decidable thing. I say it's decidable. It's something that we can determine just by like looking at the formula, so to speak. Like if I write down the formula, not A or B, if and only if, sorry, let's be formal. If and only if A implies B, you can look at that and you might be able to, and if you've taken a symbolic logic course, you might say, oh, okay, I'll write down the truth table for this and I'll see if when it's true. Or you might know that this is actually this is like a good, you might know this is a tautological equivalence and that this is true for all truth assignments, for example. And so that's how we talk about truth in zero order logic. We don't care about what A means or what B means or anything like that. But once we start talking about first order logic, we do start to care, and it becomes important that we interpret stuff. So look at this sentence that I wrote down. For all x and all y, pxy implies that there exists some z such that pxz and pzy. And you might look at this and say, well, I mean, I hope what you do is you look at this and you say, I have no idea what that means. And the reason you should be saying that is because I don't know what p means. And I don't know what universe or what domain x and y are choosing from. Are x and y letters of the alphabet, and p means that they're both vowels or something? Is that what it means? For like, and you just, the answer to is this true is I'm not sure, essentially. And more specifically, this sentence is completely meaningless. Like it has some form, it has some logical form. There's some properties we can determine about it. And for instance, we can determine that it's definitely not a tautology because I can think of a truth assignment. I can think of an assignment that'll make this false. So we can say, okay, it's definitely not a tautology, but that's not very helpful because this might be true under certain circumstances. And so what we need to do is figure out a way to talk about truth in first order logic. And this was a big thing that people were kind of struggling with in the 1930s, 1920s, the early 1900s overall. And so I'm going to give you a definition of what truth means, and then I'm going to talk a bit about the theory of truth that it relies on. So let's look at it first. So we say that some sentence, phi, is true in some structure if and only if, and this is the weird word, the translation, and I'll talk about it, of phi, so the translation of phi determined by the model or by the structure M is true. We write that M, and then here's this notation that's important, and this is called the double turnstile. This thing is called the double turnstile. And so we write that M satisfies or models phi if and only if it's true in the structure. If and only if it's true and like determined by the translation. So what do I mean by the translation? Because that's a weird thing to say. Oh, because I'm definitely not talking about translating stuff into different languages, sort of like different, like literal, like, you know, German or something. That's not what I mean. So what do I mean? So we're going to be relying on this theory of truth from a guy named Alfred Tarski. So A. Tarski. And Tarski was a very prolific and influential and important logician. And in 1935, he gave this thing called the semantic theory of truth. I'm going to write semantic theory of truth. And what Tarski said was that to determine the truth of some sentence, say we have some sentence P in our object language. Remember, an object language is something like for all x, for all y, pxy. Whoops, I messed up here. For all x, for all y, pxy. So Tarski said that given some sentence P in our object language, I should be using Q here, my bad. In our object language like this, P is true if and only if P true if and only if P true. And so this looks wrong, and because this is wrong, because there's a bit of notation I need to use here, and that's quotation marks. And so quotation marks around a sentence denote that this is part of the object language. Whereas this is a statement in the meta language. And so the classic example you'll see is that something like this: snow is white if and only if, so snow is white in the object language if and only if snow is white. This is the classic example of Tarski semantic theory of truth. And what you can think of this as is taking some sentence in the object language and elevating it up, so to speak. You're taking it out of the object language and you're moving it up into a meta language. And in the meta language, we can talk about the truth of it. And you might think that doesn't make sense. Like, why can we do that? And there's some interesting philosophy there, and I really encourage you to look into it a bit more. But for now, I just want to define what it means to translate a sentence and then talk about its truth value from there. So let's look at an example. So we have this sentence, and it says, there exists an x such that for every y, x is less than or equal to y. And then we take m as the standard model for arithmetic. And remember, m in this case is the natural numbers, and then like 0, addition, successor, multiplication, less than or equal to. Let's write multiplication like that. And these are all interpreted standardly as we understand them in normal life, real life. And so what we say is that m proves this sentence. If and only if there exists an x in the natural numbers such that for every x or for every y in the natural numbers, x is less than y. And this looks weird, I think. I think it does look weird. But what's important to note is that phi is in the object language. And this big translation is in the meta language. And in the meta language, we can give a proof of this statement. We can't give a proof in the object language, though. And that's because we don't have any idea of truth. And so don't get hung up on this idea too much. If you don't understand it, it's not a big deal. Just remember that we can sort of elevate a sentence up into another language, so to speak, into our normal colloquial English language, and then deal with our colloquial interpretations of ideas. So everyone knows what this means. Everyone knows what it means for some number to be less than or equal to some other number. So we start talking about truth with respect to that, rather than in this object language where nothing really makes that much sense. And so the other thing that's important to note is that this defines truth relative to a model or relative to a structure. So this defines truth relative to whatever m is. So if we changed m, the truth of this sentence might change. What this sentence translates into might change. A bunch of stuff can change depending on if we change m. So yeah, this is kind of our theory of truth. So we're going to move on to a couple core ideas, and then I'm going to drop off and it's going to switch over to the live lecture. So it's 2 more ideas. So the first idea is that of logical consequence or semantic implication. One sec. So let gamma be some set of sentences. So gamma is a set, I'm going to write SOS. And then let phi be some other sentence. Phi be some sentence. I didn't write this down, but phi is some sentence. We say that gamma, and this is satisfies, or other things. This can mean this has various synonyms, but we say gamma satisfies phi if and only if for any structure, if it's the case that that structure proves every single sentence in that set gamma, then that structure also proves phi. So this is like saying if we have a set of sentences, A implies B, and then like C, we call this gamma. Gamma equals this, and then we have some structure, and it's the case that M proves A, M proves A implies B, and M proves C if then M proves phi, then gamma proves, or sorry, I shouldn't be saying proves, gamma satisfies phi, or M satisfies phi, then gamma satisfies phi. And so we usually, like the real word for this is semantic implication. We say that phi is semantically implied by gamma, or that phi is a logical consequence of gamma, or what I'm going to be saying a lot is satisfied or satisfied by. So phi is satisfied by gamma, or gamma satisfies phi. I like that terminology, and they're all synonyms for the same thing. And we can also just say that gamma is a consequence of phi, but that term is a bit more loaded, I guess. So the best word, if you want to be taken, whatever, it doesn't matter. But anyways, this is a definition, and it's important. And this is called, this is the symbol V dash, or models in LaTeX, if anyone's wondering. And it's called the double turnstile again. And so let's move on to another one, another turnstile, the single turnstile. And so the single turnstile is a sentence about provability. And so the single turnstile essentially allows you to talk about proof a bit more abstractly. So we say that a sentence phi is provable from another set of sentences gamma if there is some finite sequence of sentences from gamma or from other places such that the last thing in that sequence is phi, and that any other gamma I is either from gamma, is the result of something called modus ponens, or is an axiom or tautology. So I'll just give a quick example of modus ponens just in case no one knows. So say we have something like A implies B, and we also have that A is true, then modus ponens says that B is true. That's all. And so this is the only rule of inference we actually have in sort of model or in logic, and then we kind of build other ones on top of this. But everything is derived from MP, and this is for simplicity in certain proofs about provability. It helps to have a simple proof system. But the important part is that we can talk about proof more abstractly here, because we can say that given some set of sentences, we can say, like, for example, say we have some subset of sentences of ZFC. So like say we have, like, so everyone knows like ZFC is the axioms of mathematics, blah, blah, blah. Say we have some set of sentences like, this is sort of an ill-formed example, but it's a good example at the same time. So we have some T, and it's like a subset of ZFC. Then we can say that T proves the mean value theorem, for example. And this would mean that there's a bunch of sentences in a row, and the last sentence in there is the statement of the mean value theorem. And so I'm going to give an example of this, and then I'm going to hand you over to me from the past. I'm going to give an example of a deduction, I mean. So here's an example of deduction. And what it is essentially, if we have this set is called gamma, and we say gamma proves P, if it's the case, then we can write down a deduction. And here's an example of deduction. And look, and you'll notice that it uses premises. So these are called premises, these elements of gamma. It uses tautologies, and so this is a logical tautology here. And this is a sentential tautology, actually. It uses modus ponens. It uses premises and modus ponens, and this is the only thing it's allowed to use. So that's what it does, and it gives a deduction. And so then we can write that gamma proves P. So that's it for Jesse from the future. I'm going to pass you over to Jesse from the past, and hope you enjoy the rest of the talk. There we go. Hi, everyone. I stopped record. I just started recording. I'm sorry for the first half of the presentation being gone. Anyways, I don't think I'll restart, but this is all boring stuff that you guys can figure it out. Okay, so now let's talk about models. So if we have some, this is the titular thing in model theory. It's the model, or it's like a, and so a model is a structure that satisfies some theory. So so if every sentence in some theory T is satisfied by a model, then we say that M is a model of T. And that's it. That's what a model is. And a model is a structure. And again, remember that a structure is a universe paired with an interpretation function over a language, over some language. That's it. Okay, and then now we're going to talk about a couple important properties of theories. So the first one is a theory being complete. And so a theory being complete is just a theory is complete if for any sentence in the language, either the theory can prove that the sentence is true. Oh, and this is my mistake. Or the theory can prove that the sentence is not true, or this. And that's it. And this is called the completeness of a theory, or the theory being complete. And it just means that given any sentence in the language, I can tell you, or I can prove or not prove it, or I can prove it or its negation. And then there's another notion. It's called consistency. And so it's, oops, I keep moving it. A theory is consistent if there is no sentence such that you can prove both the sentence and the negation. So this just means you can't prove a contradiction. And this is obviously super important in math. So people care a lot about having consistent languages. And this is a big, when I talk about Hilbert at the start, this is like a big part of his program in the early 1900s was to make sure that math was consistent and that you couldn't accidentally prove a contradiction. And if you guys are familiar with the principle of explosion, what it says is that from a contradiction, you can prove everything. And so that's the issue with the contradiction, is that if once you have a contradiction, you can prove literally anything you want and the whole system is broken. So we really care about having consistent theories. And so now we're going to state the first theorem of the talk, which is the soundness theorem. And so the soundness theorem in simple terms says if you can prove it, then it has to be true. And so here's the first formulation of the soundness theorem. And I don't like this formulation, but it's useful. And it's that if, oh, this is supposed to be, my bad. This is supposed to be gamma. Sorry, if for any set of sentences and any sentence phi, if gamma can prove phi, then gamma can model phi, or gamma is a logical, or phi is a logical consequence of gamma. Or in other words, there is a model that satisfies both gamma and phi. And this is called the soundness theorem. And the soundness theorem is often actually used in its contrapositive form. And so if everyone knows what a contrapositive is, which is that like if we have A implies B, this is the same thing as saying not B implies not A. And pretty much every time I've ever used the soundness theorem in real life is in the form of like if this isn't true, then you can't prove it or whatever. And so here's an alternate but equivalent formulation of the soundness theorem, which is called, I call it the soundness theorem 2, which is that given some set of sentences gamma, if it has a model, if that set of sentences has a model, then it is consistent, and that model is consistent, or then that set of sentences is consistent. And so remember what it means to have a model, which is, sorry, I don't remember what you said, model. A set of sentences has a model if if every sentence is a consequence of some structure. Anyways, so I'm going to give a proof of soundness 2. I'm not going to give a proof of soundness 1. So this is soundness 1. And I'm not going to give a proof of it, but I'm going to assume soundness 1 and give you a proof of soundness 2 because it's kind of enlightening to see how proofs in logic go. One sec. So remember, soundness 2 says if some set of sentences gamma has a model, then it is consistent. So what we do is suppose for contradiction that gamma has a model and isn't consistent. Then we say that there exists some sentence such that gamma proves the sentence and gamma proves its negation. And that's because gamma is inconsistent. So this. And then by the soundness theorem 1, which is, so we're assuming soundness 1, we have that since gamma is inconsistent, gamma phi is a logical consequence of gamma, and not phi is a logical consequence of gamma. But we assumed that phi or gamma has a model, say M. So there is some model that proves phi, and the same model proves not phi. And this can't be the case. This doesn't make any sense, because remember what our definition of truth was. This would be like saying 0 equals 1 and 0 doesn't equal 1, right? So just a complete contradiction that breaks everything. So this can't be the case. So that's our proof of soundness 2. And so our next theorem is something big, which is the completeness theorem. And this is a great theorem, and it's stated really shortly, and this is actually a biconditional. If you, one sec. So we'll just state it first, which is that if a theory or a set of sentences gamma is consistent, then it has a model. And you'll notice that this is the converse of soundness, of soundness 2 that I gave up here. If a model has a model, then it's consistent. So if a theory is consistent, then it has a model. And I think the question that everyone probably has, since they see like Gödel's name and they see completeness, they think, but what about the incompleteness theorem? How does he prove both completeness and incompleteness? That doesn't make any sense at all. That's contradictory. And so I just want to talk about it really quick. So no, they aren't negations of each other. They don't contradict each other. And what the completeness theorem says, that it says, if you give me some theory and it's consistent, then I can tell you if it has a model. What the incompleteness theorem says, this is going to be really informal, and there's like a whole bunch of extra stuff behind the incompleteness theorem. It says that if you give me some consistent theory with certain properties, then there is some true statement about the integers, that cannot be proved from this theory. So this, I should have said, if you give me some consistent theory in the language of arithmetic in LA with certain properties, then there exists some true statement about the integers that cannot be proved from that theory. And these are super different, right? Because having a model and being able to show or being able to talk about proof are like very different. So there's no real tension between the two. It's just all I want to say. And you can go and learn a bunch of computability theory if you want to like formally learn the incompleteness theorem. And you can also, there's a good book, I don't remember who it's by, it's just called Gödel's Proof, and it's like a pop math book that talks about Gödel's proof and gives you like the core theories, and it's a really interesting proof actually, and that's another reason why it's so famous. And it talks about the incompleteness theorem. So I'm going to give a sketch of completeness, and this sketch of completeness is due to a guy named Henkin, I think. Sorry, I have it written down. Leon Henkin. And he gave a simplified version of Gödel's incompleteness theorem in 1949. And Gödel actually proved the completeness theorem originally in 1930 as part of his PhD thesis. This was his PhD thesis, was this huge theorem in first order logic that says that any theory in first order logic, if it's consistent, it has a model, which is really important. And so this is his doctoral thesis. But it's like the Wikipedia article for the theorem actually says that like if you were to go back and try to read his original paper, it's complete gibberish to people nowadays because the notation is so outdated, it's ancient. And so Henkin gave a nice simplified version of this theorem. And I'm sketching a version from a book called Chang and Kiesler, a model theory textbook. And this is on page 61 of C and K. Ooh, sorry, my C and K. And so this is a weird proof, and it's quite technical. So I'm really black boxing a huge proof part of this proof. But essentially what we do is that we take our consistent set, and then we create a new language that we toss a bunch of constant symbols into. So here we toss a bunch of constant symbols, and we create some language L bar. And then we add a bunch of new sentences with these new constants from L bar to create a gamma bar. And we can assure ourselves that this is a consistent set of sentences in the new language that we made. And then this is the part that's hard, is that we can show with some difficulty and some emphasis there is a model that proves gamma bar, not the original gamma, but gamma bar. So this extended sorry, that there's a model that proves, so there's a model M bar that proves gamma bar. And then we can reduce, and again, I'm being like really hand wavy here, we can sort of reduce M bar to M. Sorry, this should have been M there, to only use symbols from L. So this means not the new constants, not new constants, so no new constants. And then, so we've reduced this model that we know proves gamma bar down to a model that doesn't have all these new constant symbols. And then we know that this is super hand wavy, that we know that gamma didn't have, like the original gamma obviously didn't have any sentences about the constants that we added in the L bar language. And so we can now say with confidence that this reduced model proves gamma, since every sentence in gamma does not involve the constants from the extended language, and M can still model gamma, and then we are done. And that's the proof of completeness. And this big theorem that I'm hand waving is lemma 2.1.3, I think 2.1.13 in C and K. And you can go read it, and it's super long, and you'll see why I didn't write it down. This is here. This is that thing. So that's the completeness theorem, and that's a great theorem. We proved it now. We're all really happy. And so this next theorem is an even cooler theorem in my view. I think it's the coolest result in introductory logic, and it's the compactness theorem. And so the compactness theorem says that a set of sentences has a model if and only if every finite subset of those sentences has a model. And this is this may be a weird statement to you, it might not be, and you might see the word compactness and you might think of topological compactness. And if you're like one or two people in this chat, you might think of compact cardinals. In which case I don't think you need to know about the compactness theorem. But these are all related. And so, and the compactness theorem essentially, well, it's a really important theorem in logic. And the way we prove it is using Gödel's completeness theorem. And so I'm going to present a proof of it. I'm going to write it down by hand because I think this is important. And it's like, I think it might be a bit better for learning if I write it down by hand. So this is a biconditional. So the first thing we're going to do is prove this direction. So let's write it like this. And this all we do is we say, okay, so a set of sentences has a model. So suppose that this gamma has a model. Then pretty much trivially, any finite subset of it, then any finite subset of it, finite subset must have a model, shares the same model, in fact. And you can verify this if you want. It's not interesting. Same model. Model. And so this is the proof of the forward direction. And this doesn't matter. It's super easy. The other direction's the actual interesting part. So let's go this direction. And what we're going to assume is that we're going to do this by contradiction. So we're going to suppose every finite subset, let's say gamma naught of gamma is or has a model. Model. And suppose gamma does not. So what we have is that some finite subset of any arbitrary finite subset of gamma has a model and gamma doesn't. Then the next step is that we say by the contrapositive of completeness, since gamma doesn't have a model, and remember the statement of completeness is that if consistent, then model. So the contrapositive is that if no model implies not consistent. This is super like ugly notation, but that's the contrapositive of completeness. And so what this says is that since gamma doesn't have a model, gamma is inconsistent. So the upshot of this is that there is some sentence phi, there exists some phi, such that gamma proves, remember the definition of consistency, or inconsistency, sorry, is that gamma proves phi and gamma proves not phi. And so this is just what it means to be inconsistent. And then if we remember a little bit back, I said that a proof is a finite set of sentences. So like a proof is like gamma 1, gamma 2, ... and it ends in phi. And this is what a proof looks like. And so what we can say is that, okay, so there are two finite, so there are finite sets, subsets of gamma. Let's say gamma prime and gamma prime prime, which are subsets of gamma, such that, and then we're going to say gamma prime proves phi and gamma prime prime proves not phi. Okay, so I think you guys might be able to, maybe some of you can see the contradiction coming up already. But what we have now is two finite sets that prove phi and prove its negation. So we can really easily see that now gamma prime union gamma prime prime proves phi, and gamma prime union gamma prime prime also proves not phi. So therefore, gamma prime union gamma prime prime is inconsistent because it proves a contradiction, right? This is a contradiction. If we can prove phi and not phi, then we clearly have a contradiction. So then by the soundness theorem, and remember the soundness theorem says that, Jesus, I'm forgetting everything today. The soundness theorem says that if gamma has a model, then it's consistent. So by the contrapositive, which is that if gamma is inconsistent, then it doesn't have a model, we can say that gamma prime union gamma prime prime has no model. No model. Model. And my negations are backwards. I'm sorry. I'll try to be better. So since gamma prime union gamma prime prime has no model, I'm going to ask you, I don't know what that means, but whatever. That we have that gamma prime union gamma prime prime is finite by definition. It's the union of two finite sets, so it's finite. And and it's a finite subset of gamma with no model. And this is a contradiction. And this is because here we have that gamma prime prime is a finite subset of gamma with no model. And up here, we suppose that every finite subset of gamma has a model. There's our contradiction. I don't know what you guys are talking about, whatever. And so there we go. That's the compactness theorem. And this is a really cool result. And we're going to start talking about some cool implications of the compactness theorem. And so I might take a 5-minute break just before we move on, just because the next part is kind of disjointed. We're going to start talking about problems. So I'll take a 5-minute break and I'll be back at 2:03, and we'll start talking about problems involving compactness. So I'll see you guys then. Okay. Hi, everyone. Welcome back. So just to recap, we've just finished proving the compactness theorem. We've proven Gödel's completeness theorem. And we've gone over a bunch of simple notions in logic. And so now we're going to talk about a couple applications of the compactness theorem and the other theorems that we've talked about today. So the first one we're going to talk about is the four-color theorem. And this is a cool theorem. I think everyone knows it. This was proved in 1976 by Appel and Haken. And they proved it for finite graphs. So they said, so the statement of the four-color theorem is that any map of a finite number of countries can be colored with only 4 colors. So here's a map of South America that I figured would be good because it has a lot of borders. And so what it says is that if I were to pick 4 colors like red, blue, green, and purple, I can color this map such that no 2 countries are have the same color. So I could be like, okay, Brazil is red, and then Peru is going to be blue, Colombia is purple, and then Ecuador would be green. And I hope I don't get anything wrong here. That'd be really embarrassing. Venezuela, we'll do it green again, and then maybe blue, purple, and then blue again. Okay, and there we go. We've colored the northern tip. Oh, I just made it apply to part of South America. Yeah, I think there's parts of South America that might break it. You're right, but for this part, it works fine, I guess. And so all we've done is that we've colored the countries, a finite number of countries, with 4 colors, and no 2 adjacent countries have the same color. Connected component of South America. And if anyone's wondering, the way this problem is actually mathematically stated is in graph theoretic terms. So if we have a graph with edges like this or something, and we treat each edge as a border between 2 countries, then we can color this graph. Oh, you're from Chile, welcome. That's cool. That's really far away. Wow. You can color this graph with only 4 colors, such that no 2 edges have a common color along them. That's the statement, the proper statement of the finite 4-color theorem, but it doesn't really matter for our context. So what we're going to prove, yeah, I was stated for planar graphs, right? What we're going to prove is the infinite 4-color theorem. So this means that if you have an infinite number of countries, or if you have an infinite and borders, or if you have an infinite number of vertices and edges, so this goes on forever and they're connected or something, then we can prove that the 4-color theorem holds, so that we can color every country or every vertex on the graph such that no 2 edges share the same color. And so we're going to prove this using compactness, and that's super cool, I think. And so the infinite 4-color theorem, here's the proper statement, which is that any infinite, yeah, you'll run out of crayons, I guess, but any infinite map of a finite number of countries can be colored by 4 colors such that no 2 adjacent countries have the same color. Apply to countably infinite graphs. I'm stating it for countably infinite graphs. Maybe someone in chat knows if this holds for uncountably. There's something called the De Bruijn Erdős theorem, Erdős, sorry. And I think this might deal with that context.
De Brown.
Oh, De Brown? Holy shit, I don't know how to spell. But whatever. It's I think ignore this. It's something Erdős theorem, and it deals with that context or that case. Sorry about that. I think so. Anyways, the infinite four-color theorem. Oh, is it really? That's weird. I wonder where he's from. That's a okay. De Bruijn or De Brown Erdős theorem, and it deals with this in like some bigger context. Anyways, so to prove the infinite four-color theorem, which is for our case countably many countries, or what we first do is we suppose the finite four-color theorem holds, and then we define the set of sentence letters. And by the way, this is like a sentential. This doesn't even use first order logic. This just uses sentential logic. But we define the set of sentence letters C, I, N, where I denotes the color. This is the color, and this is the country number. And so so like the letters, the sentence letter CIN says the nth color country is colored by the ith color. And there's 4 colors, so yeah. And then we construct a set sigma and each of these, or sigma has 3 types of sentences in them, and has infinitely many of each of them, but it has 3 types. And so the first one is what it says is that every country is colored. Essentially, it says that either for the nth country, either it's takes on color 1, color 2, color 3, or color 4. And so we have n of these for natural n. Sorry, there's someone blending. I hope you guys can't hear that. The second one just says that every country has exactly 1 color. So for any pair of countries, or for any one country, it only has one color. So that's all it says, right? This one. And then this last one just says that no 2 adjacent countries have the same color. And then what we do is we have this infinite set sigma, and we know that any finite subset of sigma is really just a statement of finite 4-color. Like it's just finite 4-color. If we take like from like 1 to like n equals n equals like 1 to 15. This is just finite 4-color theorem for 15 countries, right? And so we know that any finite subset of sigma is satisfiable by finite 4-color theorem. So then all we do is we apply the compactness theorem, and the compactness theorem says that since there's every finite subset of sigma is satisfiable, all of sigma is satisfiable by some model. And so the consequence of this is that the 4-color theorem holds for infinitely many countries. And that's the whole proof. And I thought this was super cool. This is like one of the first questions I did in my logic class, my mathematical logic class. And it's exercise something in Enderton. It's like in the first chapter. So this is a great theorem, or great little question. And I'm giving you guys a similar question, which is that suppose you can tile finite subsets of R2, the plane, with some set of polynomials, and polynomials are like Tetris cubes or tiles or whatever. It can be squares, or it can be like Tetris tiles, whatever. Can you tile the entire plane with the same set? And here's the precise statement. And like, feel free to just take a screenshot or something if you want to try it. It's not too hard. There's a proof by Koenig's lemma. That's like, you can find it on the internet, and Joel David Hankins gives it, and it's cool. But the one that I'm thinking of uses compactness. And this is a fun little proof. And so if you guys want to do this, here's a question that's in the same vein as this 4-color proof. Okay, so here ends the stuff that should be relatively tractable for everyone. And it gets into the stuff that's going to be, it's really algebra heavy, and it's kind of messy. And it's a famous result in algebraic geometry, and it's called Ax, growth, and Dick. Right? How do I spell this? Ben Dick. And this is a famous result in algebraic geometry, or it kind of looks analytic to me, or like something from complex analysis to me, but I'll state it in a bit, but it's a really simple statement. But first, we need to build a tiny bit of algebra background just so we can talk about it. And so I'm going to assume you guys from now on know what a field is, but informally, if you don't, a field is a set defined with addition, multiplication, division, subtraction. So like the real numbers, the rational numbers, the complex numbers are examples of fields. So R, C, Q, dot. So then we say that a field is algebraically closed if and only if for every non-constant polynomial with coefficients from the field, the polynomial has a root in the field. And so to give an example of a field that isn't algebraically closed, we're going to consider the real numbers. The real numbers. So, and if you take the polynomial x squared plus 1 equals 0, this has real coefficients, which are 1 and 1, or 1 and 0, sorry. And this has no roots in the real numbers. Obviously, like we all know, this has roots in the complex numbers, but this doesn't have roots in the real numbers. And so this means that R isn't algebraically closed. On the contrary, the complex numbers are algebraically closed. And this is important for this proof because this proof says something about the complex numbers. So anyways, moving on, we're going to define the language of fields as something that has addition, multiplication, a 0 element, and a 1 element. Then the theory of algebraically closed fields, or the axioms of algebraically closed fields of characteristic P. And if you don't know what a characteristic is, don't really worry about it. It doesn't come up in a major way for this proof. We're going to denote it the algebraically closed field sub P, so for characteristic P. And this field is going to consist of the field, or this axiom, this set of axioms is going to consist of the field axioms. And then it has an axiom for algebraic closure. And so this just says, it says what this says up here. Says what this says. And then it has an axiom that says the field has char P, or if the field is char 0, then it has an axiom that says this field is not char P for every P, which is yeah. So this axiom actually says, like here, it says this, like F is not char P for every prime P. And don't worry about why it's prime, prime P. And so this is what it says. And this is important sort of to know that there's infinitely many, there's natural number many sentences that say in a char 0 field. And so we're going to talk about the first theorem, which is that the theory of algebraically closed fields is complete for any prime P, or if P is equal to 0. And so remember that a theory is complete. So ACFP complete means for any arbitrary sentence var phi in the language of fields, either ACFP proves var phi, or ACFP proves the negation of var phi. I got it right this time. This is what this theory being complete means. So I'm going to sketch this proof because it relies on some important facts from algebra and some important facts from like higher model theory. But I am going to give a sketch because it's interesting. If you know anything about algebra, and if not, maybe, I don't know. Anyways, so the first thing to note is that all the algebraically closed fields of some characteristic P are isomorphic if and only if they have the same uncountable cardinality. And so this means that if they're of cardinality K, then that K is greater than the cardinality of the natural numbers. So it's uncountable cardinality. And then this fact, so this fact comes from the fact that any algebraically closed field of cardinality kappa has transcendence degree kappa, and I don't remember the definition of transcendence degree, but it's a thing, and this is really irrelevant, this part. And then algebraically closed fields are determined up to isomorphism by their characteristic and their transcendence degree, and this is by a theorem of Steinitz, and you can find this theorem, and I think I gave a reference at the very end of the talk for where I found this specific proof. And then we also note that any algebraically closed field is infinite, and so since any model of the algebraically closed fields of characteristic P is uncountably infinite, ACF is complete. And this is by a theorem called I'm not even going to try to say that, something Vought test. And even if you don't understand this proof, it's fine. All you need to know is that ACFB is complete for any prime P. And then one more important theorem, and this is a theorem that I was getting contradictory info about. So Akil Matthew, who's like this, I don't know, some guy at Harvard, he said this is due to Abraham Robinson. And he called it Robinson's theorem, and you can find some like blog post from 2013 about it. But everywhere else said this was due to Lefschetz, and it's a theorem in algebraic geometry, I think, called Lefschetz principle. And this is like a specific case of the Lefschetz principle. And it says that given any sentence in the language of fields, any sentence that is true in ACF in the algebraically closed field of characteristic 0, and specifically C, we're complex numbers, which are of characteristic 0. It's true in that field if and only if it's true in some arbitrarily high characteristic field, ACFP. And that's all the theorem says. And so we're going to give a proof of this direction. So assume phi is true in some arbitrarily large P, then it's true in the field of characteristic 0. And the converse is sort of similar. And you can find a proof of this in David Marker's model theory book, and also in a paper that I've linked at the end of the talk. So the proof goes like this, something like this. One sec. So we define a theory T, and T consists of the algebraically closed field axioms for characteristic 0 along with the sentence. And then we take T naught to be a finite subset of T. And then T naught contains finitely many sentences, and so it necessarily contains finitely many sentences that say this field is not characteristic P. So it's going to be like this field is not characteristic 1, 3, 5, these are prime P's, 7, ... up to like some n. And so what we do is we pick a prime P that's greater or equal to that n, or greater than that n. So we say large enough P. There's going to be no sentence in T naught that says this field is not this characteristic. And so by assumption, there is some model K such that K proves this, and this is by the assumption up here. And then so K necessarily proves T naught because K says something about fields of characteristic P. And so T naught only says up to fields of characteristic like P minus something, like something less than P. And so ACF, so K will prove stuff about T naught essentially. And since T naught is a finite subset of T, by compactness, there is going to be some model K prime such that K prime proves stuff about the big model T. And then since K prime proves or models ACF naught, and K prime also models var phi, or phi, we have by completeness that the ACF sub characteristic 0 proves phi. And that was kind of messy, but you get the idea, which is that for arbitrarily large P's, the algebraically closed fields prove the same sentences as the algebraically closed fields of characteristic 0. And so this is going to come in handy for our next theorem, which is the Ax-Grothendieck theorem. And so what this says, it's a really simple statement, actually. It says that every injective polynomial map from Cn to Cn is surjective. And that's like a pretty easy statement to understand. But what's interesting about the statement is that it looks nothing like a logical statement. It has no like remnants of model theory in it, or no remnants of proof theory. It's just like a statement about apparently differential geometry, but or algebraic geometry, but it looks like a complex analysis theorem, like I said. And so we're going to prove this using model theory. And so it relies on this lemma, and this is an algebraic lemma. The proof is completely algebraic, and it's in marker, again, page 61 in marker, or 43 in marker. 43 marker. And it says that, sorry, for any finite field f, it's for any algebraic closure of some finite field f, the injective polynomial, any injective polynomial mapping from the field to the field is surjective. And so this is for finite element fields of arbitrary characteristics, or sorry, just any characteristic for algebraic closures of P element fields. And this is going to come in handy. So let's go here. And this is the last proof. So what we do is we take some element in Cn, and we define f of x to be a polynomial map, or be an injective polynomial map where each fi is degree at most d. So each fi is like some polynomial, like you know, whatever, cx to the d plus da da da. And then we suppose for contradiction that this function isn't surjective. And then we define, this is the cool part, we define a sentence, big phi, to be the sentence that says that for any field k, k proves this sentence if and only if every injective polynomial from kn to kn is surjective. And I forgot to include this, but every injective polynomial with degree at most k. So here, because d is here. And then n is from, this is n. And then from our previous lemma, we have that fp clearly proves phi d, because remember, this lemma says that any injective polynomial mapping is surjective. And so, on this map is surjective. So fp must prove this for some prime p. And so by the theorem that we proved earlier, the Lefschetz principle, since C is of characteristic 0, C and these two, this field and this field, prove the same statements. And so specifically, it proves this statement. And this is a contradiction, because up here, we supposed that it wouldn't prove the statement because this is a statement about injective maps. So anyways, the consequence is that we've just proven a statement about essentially polynomials on the complex numbers purely model theoretically, almost purely model theoretically, which I think is really cool. And it's an example of an application of model theory or of logic in general, outside of where you might expect it. And it's kind of hints at maybe why you should study logic. Because if you study some other field, you'll never know when you might end up using the compactness theorem or whatever other theorem. Anyways, that's the end of my talk. Here are some references for further reading. Specifically these two papers. I really like these papers. They're just like UChicago RU papers. They are really informative, especially about the stuff that we talked about today. So that's all. I'll stay around for questions. I have all day. So if you guys have questions, feel free to turn on your mic or talk in chat, whatever.